Let's start. Hello, everyone. A little bit of introduction. I work in Google. The stuff that I do in my daily job is not related to what I'm talking about. Most of this is done in my free, fun times. Everyone has its own way to have fun. It's been since 2009, so 10 years now, that I like parallel computing and all of that. And in the beginning, I used to do this with Go, but in Python. So I already had this idea of channels and all the locking and unlocking, but if you try to do that in other languages, it just doesn't really click. When I came to Go, I found out that it was really, really nice. So I started doing a lot of parallel programming, and then I realized there was something that was in the way. I thought that using more cores would just make my code faster. Like, I had 4 cores, so it should have been 4 times faster. It was not. I encountered this monster here, which is contention. Contention is hard to deal with. So since I'm a scientist, I decided the first step should be to measure, learn how to find out what was causing my performance to degrade. And that led me to discover some of the tools that are now in Go. Weren't there in the beginning, but they are now pretty good. Prof and trace. Prof is a very, very insightful and useful tool. It's not just for the Go project, but Go has very good integration with it. Prof comes with a Go toolchain, so you can use it for everything you need. If you just run your benchmarks with this flag, it will spit out a file. And with that file, you can just go to pprof. This is not necessary anymore, and the output, and you can type web in the console that fires up. And that shows you a graph that I'm going to explain in a second. When I saw that, I was like, cool, but now I need to write benchmarks. And I'm lazy. And mostly, I consider myself a programmer just because I'm lazy. I want a computer to do stuff, I don't want to be the one doing it. So, and also, when you write benchmarks, they are artificial. You're putting your code through a workload, but that is unlikely to be the same that you're going to encounter in production. I've seen many, many code bases running perfectly in benchmarks and micro benchmarks, but being awful in production. Especially with contention. Contention is very hard to find out about with benchmarks. So Go gives you that. If you just import that package, you don't need to do anything about it. You just have to import it. So you can do underscore in the import for this. This is going to register an HTTP handler that is going to listen on localhost and will allow you to connect to it and download this file, basically. You can tell it, OK, collect all the data of the runtime for 5 seconds and just download the file. You can run this in production. It's not very it's cost efficient. It slows down a bit while you collect the trace, but while it's not running, it doesn't cost anything. So this is a very simple example with code. I just run some Go routines, and for every Go routines, I acquire a mutex, increment a variable, and release the mutex. This is one example of code that creates contention. So I was reading at the output, and the first thing that I noticed is that I spent 0.4 seconds in my function, and everything else, all the rest of the time, was spent somewhere else. So I was doing job for a ridiculous amount of time. If you expand this, the output is very verbose. You see that I was spending all the time locking and unlocking the mutex. I wasn't doing any job. That was useless. CPU is not that cheap, CPU time, especially if you do cloud, so this was not a great output. This is, of course, artificial, but I've seen stuff like that in other projects. If you're into very fancy UIs, now PeopleOff supports flame graph, so that gives you like the function that I was profiling, and then the blocks that represent how much time of that function was spent doing work, which is this bit here. Not nice, not good. If you use mutex profile instead of CPU profile, you can go even deeper, and it tells you exactly which mutex you were trying to lock that was taking away a lot of time. Please note that sometimes the information won't be given on the lock operation, but on the unlock operation. This is a known bug, keeps the runtime simple, but that gives you at least which mutex and in which position you're spending too much time on. There is another tool, which is trace. Gives you a lot more information. And unlike pprof, for which you can find many examples and you can find a lot of documentation, trace is just not documented. It was initially a tool for the Chrome engineers to benchmark and trace Chrome. And the Go team just decided to piggyback on that tool and use it to do analysis on Go. And as many tools that are engineered by the Go team, it works very well, but it's not nice to look at. So this is one of the outputs. Ta-da! And it's very useful if you use trace to see the tail latency. When you have a code that is running and is trying to serve many clients, most of the time it's going to run fine. I mean, unless you intentionally write bad code, it should run pretty smoothly. But sometimes one page, one execution, one function will run slower. And what do you think will happen? That your users will see, oh, this runs very good. Well, except about that, but who cares about that? Or will they go like, this isn't working. Why is this slow? And this is usually what a user sees. If everything works perfectly, no one will complain. But once one thing starts going slow, that's what you notice. And in this case, well, there isn't much difference here, but I have 4 Go routines that were doing something, and one took more. So you can click on the link, and it gives you a breakdown of how much time you spent and where. So this is a total execution time, and you see that there is 7, 5, 7, so it tries to group them together. And if you see here, I spent sometimes blocking, and a lot of time pressuring the runtime to schedule me. So I was not working. I was just telling the runtime, can I have the mutex, please? Please? And that is what I was doing. These, if you don't use trace regions, is also automatically generated, so you can get the same output without changing your code. This just, you can get that by just using the trace tool. And it gives you the same breakdown. It's very insightful. And when you see this stuff, you see that trace actually has another tool, which is this. This is the trace tool inside trace, because we don't like to repeat ourselves. And in this section, you can see what you were doing or not doing. For example, at this point, this proc was doing nothing. This is useful in some cases, not for contention, but can help you to understand, for example, where you're serializing execution. Sometimes when you use a channel, especially an unbuffered channel, it happens that all your routines will actually hop in different processors, but they're never going to execute at the same time. So trace gives you this information, but it's not very easy to find out that you're spending time on mutexes. So keep this in mind, but not for this case. Once you're done measuring, and measuring is very important, and we'll see why, you might want to stop for a second and understand that you can never measure something for free. While I was preparing this talk, I was trying to instrument all my code in order to have perfect information and all the data that I needed to show you something, and I found out that I was benchmarking the trace tool. So I was measuring so in depth that I ended up finding out that the trace is very efficient. I had no information on my code, but I mean, trace is a good library. So beware to not put too many trace regions or trace code in prod. Little bit of warning. I'm now about to tell you how to address those problems. Do not implement the stuff that I'm about to talk about before measuring. This stuff can make your code slower or less readable. So just do this when necessary. This is a nice schema of 3 Go routines writing to a channel and 3 Go routines reading. Beware, this doesn't need to be a channel. It could be a struct with a mutex on it. It could be something, a contended state, a variable with a mutex I use to synchronize, but it's just some sort of writers and readers approach. This is very common, especially in Go, because we have this concept of data pipeline and sending data back and forth. Keeps the code readable and simple. This is how the hardware actually sees this thing, because all that stuff means that the hardware is put under a lot of pressure to find out a way to deal with it. The runtime is going to have to find a way to schedule the things. And as you have seen in the previous talk, it's not that simple to find out who's the next routine to be executed. This is expensive. Well, I was about to introduce channels, but I think that's done. The most important thing is this. The fact that you have a mutex, and you are contending on it. So, first solution is to shard your state. So instead of having just one single state, you can have 2. And when you measure your code, you're in production, and you see that actually you have like producer and consumers, and more or less the producer are 2 to 1 in a ratio with your consumers. This is usually common when you have a stable queue. So all the items that go in actually go out. You don't spend time pressuring, so the channel is never full, actually. And you can split the work because it's never going to happen that this one, for example, is going to take a lot more time. This is common, especially, for example, in HTTP servers. You just get the job. Every HTTP request is going to consume the same amount of CPU, so you can reason about it. If your workload is very not well distributed and some routine can take more time, do not use this approach. But the nice thing about this is that one entire cluster could go down, and you can load balance on the others. And the other nice thing is that you contend a lot less. If you see that you are contending too much, you put down 4 of those, and you have divided your contention by 4. It's just a constant, and you can just take off your runtime cost. The other solution is to batch. So batching comes in place when you don't care about latency, and you don't care about consistency. So sometimes you just need to do a lot of work, and at one point, all the work that you've done needs to end up in the same place. Let's say, for example, you need to concurrently fetch a lot of URLs and count the links in them. You don't need to update the count of the links at every time you find a new link. You can just say, OK, every 7 pages, I can just keep a local counter and push it to the central state. This allows you to just synchronize a lot less. Because you're doing your job. You're in your local Go routine, you just use local variables, you don't have global state, and you're fine. This bit has some problems if you need actual consistency, because you don't want to perform the same thing in 2 different Go routines, or you don't want your state to be too much out of date. So for example, if you are a bank, you don't want someone to be able to spend the same money twice. So this is very effective, but beware when you use this. It's more effective than the other one because you don't need to know the workload or how long a Go routine is going to take. Now, mutexes are a little bit faster than channels. They don't provide as many functionalities, as many methods, but they're lightweight. So when you have a channel that is just not fast enough, you can try and replace it with a mutex, but you have to be aware about other things, so that when you shard your state, let's say that you have a dictionary in which you have to insert words. So you write this awesome library, and you say, how should I break down the alphabet? Well, I have the first letter. I can use that as a key. So you can say, I will keep a bucket of words, so a map, for every word that starts with a certain letter. So I'll have a hash map for all the letters that start with A, and so on. This might seem like a good idea, but there is a zip flaw that is going to bite you very hard, because you write this dictionary, you know the alphabet is divided in different letters, and you're good, until someone tries to use your dictionary to, for example, hold all the Java packages that your company uses. And all Java packages start with C. So you see that one mutex is going to burn up and take down the entire CPU time, and everything else is just going to be there waiting for input to come. So measure and beware of what you're doing. One other thing that is there in the standard library is read-write mutex. This comes in when you need to write just every now and then to the central state, but you need to read a lot from it. This allows you to have very, very fast code in the read part that should be the hot one. One comment, mutexes are fast. I've seen people trying to say, oh, so I have a contention problem, I should probably remove the mutex. That is not the good approach. Do not try to be faster than your runtime, because if you can manage contention, if you're able to divide contention as I just told you, mutexes are never going to be slow. Mutexes are always going to be fast enough, because the entire code that you're going to execute fits on this slide. If you have zero contention, this is what a mutex does. It compares and swaps the state from unlocked to locked when you acquire it, and decrements it by 1 when you release it. That's it. You can't get faster than these on modern hardware. So do not try. This is the end of the safe zone of my talk. This is stuff you can reason about. This is intuitive stuff that usually you can find out by yourself. But then there is something else, because hardware is not ideal. And I'm going to show you a little bit of code. This is the function, and I have a weight group. I add to the weight group as many CPU cores as I have. I spawn that many coroutines, and then I do this, which is I take the slice of one type, which is one of those, and I access that slice in a different position. So every coroutine, let's say I have 4 cores, I have 4 coroutines, each one of them is writing a different index of the slice. So coroutine 0 is writing in index 0, and so on. And they're going to write a lot to that slice. And I use 3 different types. uint8, uint32, and uint64. One of the coroutines is going to write 8 times more than the other. So this one is writing 8 times more than this, because it's more bit, it's bigger data. So which one would you say is faster? The one that writes less, or the one that writes more? On this laptop, this is an Intel i7 laptop. So who says the faster one is the one that writes less? Okay, the one that writes something in between. The last one? Would you be able to say why? Because it's indeed the last one. The one that writes more is the one that is pretty much faster on 64-bit architecture. Is that a question? So you say that there is contention on some area of the memory because the lock protects 64 bits? Almost. So the problem is that this is your actual CPU and your memory model. This is what you should always keep in mind. Every core has its own cache, and those caches have caches, and it's all caches all the way to main memory. When you content that bit, when you write to the same slice, you cannot write 1 byte at a time. Our modern processors are not made to write single bytes. They are made to write bigger slices of bits. And what happens is that every time I tried to change my local slice, my local number, I needed to go to main memory with the first example, the one that wrote just 8 bits, because someone else was writing in the same cache line in another core, so we needed to synchronize. That is called false sharing. So if you have data that is too little and actually ends up being the same cache line, you're going to contend as if you were writing to the same integer. Because our CPUs are not fine-grained. They cannot deal with that granularity of data access, especially not concurrently. That is false sharing. It's pretty easy to get rid of. You just don't use some entries of the slice, or if you have a struct, you can use underscore fields in the struct. They are not accessible, and they are padding. So they keep memory away from being falsely contended. But sometimes you have actual, real contention. So if you have a read lock, so read-write mutex, every time you need to acquire a read lock, you need to inform the lock, I want to read. So what you're going to do? You're going to write. So every time you acquire a read lock, you will write to memory. There is one more reader, which, for the example before, means that if someone else is trying to read the two, you're going to the main memory, or a cache line many layers above, to say, hey, can I read? Yes, of course, you can read. And that takes a lot. It can be thousands of cycles wasted just because you wanted to read and you had to write for it. When this happens, you need to do smart things, sometimes way too smart things. If what you need is a map, so if you have a hash map with a read-write mutex that protects it, there is something in the standard library that can save you. This is SyncMap. SyncMap removes a lot of cache contention problems, but it comes with a cost. A SyncMap is a very complex data structure that avoids cache contention, and to do that is basically struct with methods that receive pointers to struct with an atomic value that points to a struct, with a map that points to a map header that points to a hash table whose elements are themselves pointers to atomic pointers to interface values that point to concrete values that might themselves be pointers. So we're going to spend a lot of time resolving addresses. So just use these when necessary, and after you introduce these, try again, measure again, because it's not necessarily a better idea. Just, this is good up to a point. So, I was doing my research, I was trying to get rid of contention, and I got to this point and I was like, what if I don't need a map? What if I want something else? What if I want to have a central variable that I need to read many times, but I almost never write? There are ways. You can use the atomic package, and if you go to the atomic way, most of the time, if you need to synchronize a struct, you need to use unsafe pointers. And it's like juggling razor blades. It's not like it's impossible. There are people that can do that, but most of the others have stopped because they lose some fingers. So when you start doing atomic operations and you start going that direction, the race detector bails out. So the race detector will just say, oh, you're using atomic and unsafe, how cute. But I have no idea what you're doing, so no races. Everything is good, it's fine. Even if you have an explicit race on one of your variables, the race detector is just not going to tell you anything. And then there's more. If you use them wrongly, the compiler might reorder stuff in some architectures, so fun stuff, especially debugging it. But if you really have to, I have an example. So the read part, which is the one that you're going to do more, is very easy. You just atomic load it. Now, I omitted the type, but after the load, there is another word. It's usually load int 32, load int 64, but you can atomic load something. And you give it an address. When you need to write, it's slightly more complicated, because you need to load the value, change the value with the operation that you want to apply on it, like, for example, increment it by 1, but then you need to say, is this still the same? Did someone increment it in the meantime? If so, I need to redo and retry. So you put stuff in a for loop, and you just go, OK, change, Is it the old value? If so, set it to the new value and break out. Otherwise, reload, change, retry. As you can see, this stuff can be time-consuming and potentially can lock your CPU for a long time, so just use this sparingly. And be aware that this is not still safe. There is another problem that might occur. I'm not going to go into detail in explaining what an ABA problem is, but just know that this only works if your data is monotonic. So if there is no one else decrementing it, it's just going up. This is a bit of history that I found interesting. So weight group, who here has used at least one weight group in their code? Okay, it's pretty common data structure. It was rewritten from using mutexes to atomics. It went so much faster, and it was so good that a change was kept. This happened in 2011. And this is very scary. Random-looking memory corruptions started appearing. And nobody couldn't find out why and when. Until 2014, in which the bug was actually fixed. So we're not talking about newbies here. We're talking about some of the best programmers in the world, especially for concurrent programming. I don't know how many of you have heard of Dmitry Vyukov, but he's like a guru in this stuff. And this bug was introduced and fixed by him. And this is the code that was affected by this. Basically, there was this if. Runtime atomic add stuff equals this. This line introduced a race condition. Can you find it? I stared at this. I was staring at this, and I was like, no. I have no idea what is going on. And the patch was to store the comparison variable before this happened, because otherwise there were some spurious wake up, because in the original value, these could have changed while the CPU was executing the comparison. This stuff makes you faster, but it's so much harder to deal with. So do it sparingly. I suggest everyone to try it out, at least read some things. It's very fun to do. Just don't push it to production on a Friday. And that was my talk. Thank you.
Thank you very much. Any questions? For the bean? Come on.
Or I can try to reply. Oh, question.
So maybe it's, thank you for your really great talk. Maybe it's a simple question, but in what situations on production do you really need to use atomics? After your talk, I can tell that there's any situation that you need to use atomics because it's pretty unsafe, as you've shown.
You never need to use atomics. You can just install more CPUs. But sometimes you cannot really put more CPUs on your server. So sometimes you're like, okay, I need to optimize. How should I do it?
It's a question about the hardware. So you need to use the atomics in case when you cannot handle more good quality in case of hardware.
It's more like, at one point, your code is going to be slow. You have more users, and you do a benchmark. You test performance, and you see that one of the things that is taking away more time is synchronization. So at that point, you have two choices. You either duplicate your server, buy more hardware, and keep the code with mutexes. Yes, that's the right answer. Or sometimes you can't even do that because you have a lot of stuff, and you can't just keep buying more hardware just to spend 20% of it locking a mutex. And that's the time where you take someone that knows about atomic programming, you put them in front of a screen, you provide them with food and a lot of coffee, and you just wait.
Okay, thank you.